Greater than. Greater than? What I did is I made a file. Wow. Yeah. I was wondering. You did?
Well, y'all don't look like you've lost a whole lot of sleep. Well, you're well practiced then. Congratulations. So, okay. How many of y'all got the lab done? Have you answered the questions to phase 2? If you haven't, you aren't done. I mentioned to you those questions are not trivial, even though I've done a whole lot of answering the questions for you by giving you the linking lecture. You're not done until you've done that, and that's going to take a little bit of digging. How many of you have gotten it to load onto a board? How many of you are really struggling and thinking you got your compression done, but it's just not loading onto the blasted board? Alright. Rohit's a lot of help, isn't he? How many of you don't know who Rohit is? Alright. You have been going to lab. Okay. Anybody have any questions they want to bring up? We all know there are those in the class with issues. If you want to try to address an issue, I can decide whether or not I'll table it till after class. Okay. Yeah, Levi.
When I use Visual Studio 2008, it has warnings on F open. So
Yep.
right back down to 2003 it doesn't.
Uh-huh.
So that's explained when you use F open _F, because it doesn't recognize it in 2003 or 5.
Okay. So the question is, how do you get rid of these blasted warnings under Visual Studio 2008 that's complaining about F open? There's a way around it. If you look in the help files about these security warnings, there are some preprocessor directives you can turn on that will turn off the error messages in Visual Studio 8. They will not affect Visual Studio 2003. So you can still use fopen and have neither of them yell at you. I hereby and forthwith in perpetuity thus declare it is legal. Your code has to work on a lab machine. All right, well, I will leave it at the ambiguous statement of it has to work on a lab machine. Another question? All right, onward. Okay, so this is probably one of the first theory lectures we've had. We've been doing nuts and bolts, nuts and bolts, nuts and bolts, nuts and bolts. So here we go with a theory lecture. The next two are theory lectures, even though the next one is going to feel kind of like a nuts and bolts lecture because it's my introduction to how to program in C. And Ada, and Java, gag, and Occam 2, good programming languages. But anyway, we're going to talk today about Chapter 2. If we get through this, we'll start talking about Chapter 3. So you should be reading Chapters 1, 2, and 3. As soon as we get through Chapter 3, you will be neck deep into Lab 2. We'll barrel on into Chapter 4. Anyway, keeps on going from here. So what I'm trying to impress on you is that I'm not going to spend a whole lot of time in lecture on the first few chapters of the book. We will be completely done with this today. Chapter 3 may take a lecture period, may take more, depending on how things go. Chapter 4 is another lecture or two after that. So just be reading the first few chunks of the book. Some people find it dry. I happen to think it's a good book. Okay. A few notes. When you're running Lab 1, when you push the little reset button on the TS7200 board, that doesn't clear out RAM. Okay? So there are situations to where you could run a program that's working correctly, then you hit the reset button, rebuild your program on the host using a different printf, and download the program again, and it's printing out what it was printing out before. The reason why is because if your downloader isn't working correctly, if you don't actually overwrite the old program, your loader will attempt to load the new program. It'll jump to RAM that still holds the old program. Okay? So the only way to clear out the contents of RAM is by doing a power reset, a hard reset. So toggling the power on the board. Sometimes this messes you up. Sometimes. Okay? So just be careful. All right. Another good quick check on your decompression algorithm, or on your compressor. If you take your p.bin and you run it through gzip, and you take your p.bin and you run it through your compressor, and if your compressor tells you you've compressed the file down to about 100 bytes, and gzip says it takes about 60K bytes, guess what? You're not better than gzip. You will not win compared to gzip. Okay? gzip will win. Gzip is the same algorithm as WinZip. Okay? That algorithm implements a run length encoding, but it does it much better than you do. So if your files are coming out smaller than gzip, your compressor's wrong. Okay? So there's a sanity check for you. If you've written an expander instead of a compressor, I can write one of those. That's pretty easy. Okay. Remember to check out boards. Remember to answer the Phase 2 questions. Okay, Chapter 2 material. All right. What is the goal of a real-time system? What's the goal of real-time system design? We want to be able to produce a system which is guaranteed to meet its requirements. If you're an engineer and you like to do things with computers, you should shudder at that term. Guarantee, computer. Those two things typically do not go well together at all. Ask the guys who developed the software for the Mars rover that got stuck on a rock back in 1997. Guarantees are hard to do with software. How do we go about doing it? There are multiple developmental models for doing software development that are not just specific to embedded systems, but that apply generally to developing software. There's a waterfall model that says you start with requirements analysis, you do a high-level design, you do a low-level design, you go to implementation, and then you go to test. Anybody see anything missing in this? Yeah, any feedback paths? How many of y'all get your program right the first run through? Yeah. Especially considering we haven't even loaded on the board yet. Yeah. So, obviously there's feedback paths that I'm not showing in this diagram that take you from any one spot back farther. The farther down you get in this flow, before you detect an error that causes you to go back up higher, say to requirements analysis, the more expensive it gets, the more time consuming the iteration gets because you've got to repeat a whole lot of steps. Okay, so we're going to talk about what each of these boxes mean in the context of an example. Okay. Let's suppose we are traffic engineers. We've got an intersection of two roads. You know, my outstanding artistic abilities here. Boxes and lines. We've got cars coming this way and cars going that way. We want to put a traffic light here that signals the cars on both directions in this intersection to stop and go. Okay? So, let's just talk about this a little bit. What should this system do? What should the system do? Traffic light control system. What should it do? So I got one comment that said, and another one that says, stop one way while the other one goes. Okay? What else? Any more profundities like Give enough time for the cars to get through. Okay. Worry about how many cars are going on. Okay, so worry about the flow of traffic and make sure that if you want to weight the number of cars that get through one way or versus another way, make sure you manage that. However, if you're designing a system, you want one of your requirements to be titled "Worry about this." How many of y'all like your computers to worry? So, I worry about my computers. I don't want my computers to worry about me. The phrasing of the requirements is also important because it can be ambiguous. What does it mean exactly to worry about this? You did say it informally, and we're having an informal discussion, and that's completely fine because we understand what you're talking about. However, when you're trying to be really nitpicky about what your system is supposed to do, having a computer worry doesn't mean something specific to anybody. Okay, so there's ambiguity in the way that we talk, in the way that we phrase things, in the way that we state things. Cars should be able to go through the intersection. At the same time, if my requirement is that cars should be able to go through, does that mean I should let east-west guys go through the intersection at the same time as north-south guys? No. Why is that a problem? Because I don't want to die. Okay? Requirement number 1, people should not die. Okay. So, how about here? At a 50,000 foot level, we don't want to have any wrecks. Right? One good way of designing a traffic light controller that will guarantee that nobody will wreck. Anybody give me a good one? All reds, all the time. Nobody goes anywhere. That's why we come in with requirement number 2. We want to maximize throughput. What we mean by maximizing throughput is we want cars to be able to go through the intersection. Ideally, we want the cars going east and west to not have to worry about the fact that there's a north-south. We want all those guys to be able to go through without ever having to stop. Likewise, we want all the guys north-south to be able to go through the intersection without having to worry about the east-west guys. But because of the fact that we have number 1 here first, no wrecks, we've got to compromise. So somehow we've got to make some compromising rules about how do we establish a traffic light that will ensure that we don't wreck. At the same time, we maximize throughput. Okay. When we're talking about requirements analysis, these are 2 different types of requirements. So the first one is an example of a safety requirement. Don't let bad things happen. That's a safety requirement. Okay. Number 2 is a liveness requirement. That says eventually good things will happen. Okay. So don't let bad things happen and make sure that something good does happen. Okay. So we want to be able to understand what our system is supposed to do in terms of what we want it to do and what we don't want it to do. And we split things up into safety and liveness in that way. So we're going to talk about specific requirements for the traffic light. So we're going to refine these requirements. Here's a couple of refined requirements that I'll give you guys. How about we say we will never allow the 2 traffic lights to be green at the same time. Okay? Safety or liveness? Why is it safety? We don't want to die. Okay. Only green, yellow, red cycles are allowed. Okay, so any one particular traffic light can go from green to yellow, then to red, then green, yellow, red, then green, yellow, red. Why do we want to have that requirement? Don't you like random changes in your stoplight? Red, green, stop. Yellow, then to yellow. We want to be able to convey to the users of this system how to use it. So it's got to have a certain order into things. We understand traffic lights are supposed to go in a particular order. A particular traffic light cycles in that order. Okay, hold it yellow for 2 seconds before we change to red. What is that requirement there for? Okay, so it acts as a buffer. So it allows those cars that decided they wanted to floor it instead of stop on the yellow to get out of the intersection before we have a violation of requirement number 1. Okay? Other requirements. You guys think of anything else? What kind of requirement? What other detailed requirements do we want to impose on this system?
Never stop
Never stop.
being on.
Okay, system must always be on. Okay, if system cannot be on, then blink red. Okay, all right, what else? Can you impose a requirement on a pedestrian? No, I'm not saying that was a bad thing to say. But what I am saying is, let's phrase the context in your discussion. Phrasing this in terms of pedestrians is a good idea. But we can't impose a requirement on a driver. We can't impose a requirement on a pedestrian. So how can we impose a requirement on the system in the context of a pedestrian? Okay, so there's buttons that the pedestrians can notify the traffic light saying, I want to cross. Okay? Yeah, so we have little pedestrian lights that indicate the whether the pedestrian should go. The green dude walking or the red light saying, the red hand saying stop. Okay? Have we talked about a throughput requirement yet? Have we talked about a liveness requirement? How do we guarantee that cars are able to go through eventually?
Measure the time it takes for a car to go through. And
Okay.
your green lights on that one.
So we can measure how long it takes a car to go through the intersection and associate the time that the green is green for that amount of time. Okay? So let's suppose it takes 30 seconds for a car to go from one side of the intersection to the other. Supposing it was stopped, and that's how long it took to clear the intersection when it sped up and went. And we could even with that guarantee that the guy that I was driving behind on Sunday night, he'll even get out of the intersection. Okay, so if we know that piece of information, what kind of requirement should we phrase?
Green light must be on for at least 30 seconds.
When we turn to green, the green light must stay on for at least 30 seconds. Okay? If you want to maximize throughput. Okay, put sensors in the road. Let's suppose you got some fancy image processing something sitting on top of the lights that can detect the presence of a car far back enough. Okay? So what will your sensor tell you?
You can do it a couple ways, but like you could, if there's a car in such and such position, you can wait long enough that that car gets through.
Okay.
And wait until there's no activity in that for so much time.
Okay. So, two options with the sensors are number 1, wait until there's nothing left to go through the intersection, or 2, let enough cars over, and by having the sensor you can quantify enough. Because the sensor, you can get some measure of distance and how far back, how many cars are you letting through, and so forth. Okay? How many of y'all have ever pulled up to a red light, and it's red, and there's nobody going the other direction, and you just want to scream? How many of y'all think that's a good way of maximizing throughput? Not a good way. So therefore, the sensor, I would say that the primary responsibility for the sensor is to allow us to prevent stopping cars needlessly. Because if there's nobody coming the other direction, why should we stop this direction? If I'm pulled up to the intersection and I want to go, but I'm stuck at a red light and there's nobody going the crossway, ideally a sensor would be able to detect, well, I shouldn't trip green going this way based on time. I should trip it based on the fact nobody's using this intersection from the direction I'm currently allowing. So swap the sensor. Okay, so here's a few more that I tagged on there. How about no yellow, yellow? How is no yellow, yellow different from no yellow, green? Or no green, green, sorry. Why do we need to say no yellow, yellow when we already have no green, green?
yellow might be on for a long time.
Is it redundant? Does this say anything different than saying no green, green? Is this requirement necessary?
You don't know how stuff absorbs.
Okay. Okay. What should I have a requirement that says no red, red? Okay. We want to have a red, red for a little bit of a time while we wait for the guy that slammed on his gas pedal to get through the intersection and he didn't really have enough time. And he got through there on the yellow. He started in there, but it turned red while he's in the middle of the intersection. We still want to hold the other direction red till bozo gets out of the way. Okay? How many of y'all are bozos? Okay. Don't be a bozo while you're driving. Okay. So stay green for a maximum of 45 seconds or until no cars are coming in the direction you're green. Don't hold red, red for more than 2 seconds. Why do we want to say that requirement? Still want people to go. Okay, but so what does that explain to me in a little bit more detail? What do you mean by we still want people to go? Don't hold red, red for more than 2 seconds. So red, red's a good thing for a little bit of time. Okay? It serves the point of satisfying a safety requirement, but it impedes liveness if we hold it for too long. So we're going to quantify enough of red, red is 2 seconds. Okay? After that, we don't need it. Okay. Hold red, red for at least 2 seconds. Wait a minute. Didn't we just say that? What's the difference between 6 and 7? Okay. So if I say, do I need 7 if I have 6? So you're saying I should replace them with hold red, red for exactly 2 seconds. Okay. Does that say when I should hold red, red? It just says that I need to hold red, red. What I'm trying to make you guys think about is that there's particular little persnickety details when you're phrasing requirements, and sometimes you can get yourself into trouble. Now, tell me, do these two things contradict? Don't hold red, red for more than 2 seconds. Hold red, red for at least 2 seconds. Okay?
Well, I think they're contradicting.
Okay, Mitch, why are they contradicting?
Replace the word more with at least, and the two phrases are identical besides the don't.
Mm-hmm.
So you're saying one thing and you're saying the not with that thing.
Okay, now you're applying Boolean logic to requirements. Are you turning this thing into a math problem? You're trying to apply De Morgan's to requirement 6 and get you requirement 7. Okay, now you're talking like an engineer. Okay, as opposed to an English major. Got nothing against English majors. They serve good purpose. Sometimes I need to talk better myself. Okay, so can you do math on requirements?
Yeah.
Can you apply De Morgan's to English? Have you ever taken a philosophy class?
No.
Philosophy classes are cool. Did you know that philosophy and math used to be the same subject? And digital circuits grew out of it. All that stuff's the same stuff. When y'all go to graduate school, those of you who are already in the graduate school know all about this, but no, okay, no, you don't. Because they replaced the blasted analytical section on the GRE with a writing section. So it used to be these fun little logic puzzles that you could go through and apply Boolean logic to and figure all these puzzles out, figure the answers out. You know, computer scientists could eat those things for lunch, but then they made us write essays. Yeah. So, natural language, when you're phrasing requirements in English, sometimes, you know, when you start to say, okay, is this requirement ambiguous with that requirement? Well, let's suppose we had variables here, and we phrased this as less than or equal to, and that one is a greater than. And we said A represents the time the light's red, B represents the time the light's not red, A less than B, A greater than B, or, we can reduce that down to a math problem. But it takes some debate, some understanding, some in-depth thought on trying to reduce this to a math problem. Oftentimes, English statements you can't reduce to a math problem. And when you're trying to determine or prove or guarantee that your system will meet its requirements, having a mathematical specification of your requirements is much better than an English specification, because it doesn't take a room full of people to say, well, maybe, I don't know, is this met? I don't know if it's met or not. So we scratch our heads in the debate and whatever, but if the requirements are phrased mathematically, there is no ambiguity, there is no debate, it's just yes or no. Did it meet it? Yes or no. So that becomes a point of design that we're trying to convince industry to adopt, but they haven't done it yet. Okay. Liveness versus safety requirements. So we can categorize requirements 6, 5, and 3 as liveness requirements, 7, 8, 4, 3, 2, and 1 as a liveness requirement. So requirement 3 up here says, hold it yellow for 2 seconds before switching to red. We say that's a liveness requirement and a safety requirement. How is that so? So how can you interpret 3 as a liveness requirement? Hold it yellow for 2 seconds before you switch to red. Okay, why is it a safety requirement? Okay, so we prevent wrecks by making sure that cars get out of the intersection. And we allow cars to get out of the intersection by allowing cars to get out of the intersection. So you can't have requirements that are both safety, that both impact safety and liveness. Okay. Questions when you're developing requirements. Are your requirements consistent? Are there any contradiction? So we talked about 6 and 7 could potentially conflict with each other. They almost do, but they don't quite. Because of the fact, if we had another requirement that said, you cannot hold red for 2 seconds, then we'd have an inconsistency. Okay. Do the requirements achieve the goal of the system? Or in other words, have we covered what we want the system to do, what we want the system to be, with the requirements that we've said? Do we have enough requirements? So do they contradict? Do we have enough? Are they sufficient? Are they ambiguous? Can we interpret any requirement in multiple ways? So all these questions arise during requirements analysis and need to be addressed. Requirements analysis is the process whereby you try to address all of these issues. So we're not going to talk about the details of requirements analysis in this class, other than this example that we just talked about here. But just be aware that when you're doing system design, especially safety critical systems, you go through a whole lot of details of requirements analysis. Yeah.
I just want to say a question too. How do you know that without just trying to?
So question 2, how do we know, do the requirements achieve the goal of the system without actually building it? That's a good question. And there's a lot of study going on to wondering whether or not my requirements represent a valid representation of the system. You can perhaps, if it's a big system, build simulators beforehand and attempt to check to see if the simulator meets the requirements. And if the simulator meets the requirements and the simulator actually does what you intended to do, then yeah. But there's a whole study of verification and validation. Verification attempts to take your requirements and see if your system that you're building meets those requirements. Validation attempts to see if your requirements are correct, if they actual model reality. And correspondingly, the system you build, is that what you intended to, or what you actually wanted. Both of those are difficult problems. And there aren't really good answers right now. Okay, so if we move from the requirements phase to the design phase, what do you do when you're designing a system? Well, we're going to start with a context diagram. What is a context diagram? A context diagram shows the system in the context of its environment. So the system has inputs and outputs. What are the system's inputs? What are the system's outputs? We just use the system as a box, and we say that it has a timer coming in, it has a signal going out to one traffic light and a signal going out to another traffic light. The two light signals can have a signal that says red, yellow, or green. Okay? The timer is just a clock we apply to the system so it knows how much time is passing. Okay. We have to make sure that the timer clock is of sufficient resolution. So in other words, if we have a timer that we supply that counts in terms of minutes it will be pretty hard to count whether or not we've held the red for 2 seconds. So we have to have enough resolution to be able to meet our requirements. Okay. Context diagram shows the boundary of the system with the inputs and outputs. Then we go on to decomposition, where decomposition is how we examine what that box is, the system. So what we're going to do is we're going to decompose the system into we have this internal clock that's driven by the external clock. We'll call this more like a counter as opposed to a clock. And then we have a finite state machine that models the behavior of our system. So our finite state machine, let's consider 2 separate finite state machine models of our light controllers. We'll have one for the first light and one for the second light. Okay? So we'll define 3 states for this traffic light. One where it's in the red state, one that's in the green state, it's in the yellow state. Okay? And we just cycle through this pattern. We have triggering logic on the transition saying why do we go from one state to the next. And we have outputs being asserted on each state. Mealy machine or Moore machine? The output on transition or the output in states? States. We're outputting on a state. So is that a Mealy machine or a Moore machine? Moore machine. Okay. So in the red state, we say R. That means we're sending out the L1's output signal, R. So make the light be red. In green, we output the G. That means make the light be green, similar for yellow. Okay, this transition rule right here to go from red to green. So light 1 goes from red to green when light 2 has entered the red state and 2 more seconds has expired. So if we get a signal that says light 2 entered the red state, wait 2 more seconds, then we transition to green. Why do we go from green to yellow on light 1? We go from green to yellow either when 45 seconds has expired or there's no cars in my direction and the other light has cars. So we use the sensors to indicate whether or not cars are present. Okay? Once we're in the yellow state, we stay in the yellow state for just 2 seconds. There is no conditions here except for just wait 2 seconds, then transition to red. Okay? Light 2, we have the same thing. Red, green, yellow. Similar rules for transitions except for querying the other light sensors. Okay? So this is a pretty elegant model of what the lights are supposed to do. We just have one state machine for this light, one state machine for that light. These 2 state machines talk to each other, and we assume that at runtime they execute in parallel. So sharing variables, execution in parallel, that goes beyond the basic finite state machine modeling paradigm. What we do with this is we have to use another formalism called state charts. State charts allows us to execute 2 finite state machines in parallel and allows those 2 machines to share information. So we can use a state chart approach for modeling those. We're not going to get into the definition of state charts. If you want to do that, take 7780. Okay, high-level design. The goal of high-level design, so we've talked about design here. With design, you want to model your system, figure out what the system's supposed to do, how it's going to do it. Okay? The waterfall model we showed had high-level design and low-level design. We don't really have a justification for splitting these 2 things up with our simple little traffic light controller. But we'll talk about what you're supposed to do in high-level and low-level design. With high-level design, we want to identify their modules. What are the modules? You remember how I showed in the first time when we were talking about FIFO, like the second time we had class? We had the wall, we had the FIFO implementation on one side and the client code on the other side. Well, you want to figure out where to put your walls, where to group together stuff, and to identify this is a module, this is another module, and these are the interfaces between them. Okay? Identify your chunks and identify how you're going to have the chunks talk to each other. What defines a module? Well, you define those around groups of cohesiveness. So you group functionality by cohesiveness. What does cohesiveness mean? How tightly integrated or stuck together different chunks of stuff that you're doing are. That's a really general phrase, and it comes by practice and just by experience on what you're doing. But if you're thinking about code that uses a linked list all the time, you might make a module that defines a linked list and let that module be used in multiple locations. That way you can limit the cohesiveness of the linked list to the linked list module and allow other interfaces so that they can just access the services of this linked list. That way you reuse your code in multiple places You localize everything down to the point of your module. We'll discuss more about modularity and cohesiveness and all of that when we're talking about Chapter 4. Low-level design, that's where you dig into each of the modules and you design those module details. Now, for what we're doing, for our traffic light controller, our system is too small to actually need both high and low-level design. Implementation is where we code everything up. How do you code up a state machine? Use a switch statement. Problem is, we've got two state machines and they run in parallel. How do you implement that? Then you've got a sequential processor. Well, it's kind of challenging. There are ways of dealing with it. I'm not going to tell you all about that, but there are ways of taking parallel finite state machines and composing them together and creating a single finite state machine out of them, and then you can code up the composed result. But basically, ideally what you would use is a tool to model your state machine, and you'd push a button and it'd write the code for you. Okay, testing. What do you do the testing in the testing phase? Well, that's pretty obvious. Run tests on your implementation to see if it works. Evaluate it in their different situations. Deploy it on your test track. See if it's going to do what it's supposed to do. However, that testing isn't going to tell you a guarantee. Testing that you do in your lab will never guarantee anything. All that it will guarantee is the one test that you run, that you did run, will work under the situations under which you tested it. In order to be able to offer some type of guarantee that your system will work, you need to use mathematics. What type of mathematics do you use? They're called formal methods. There are different formalisms for phrasing system models and queries against those system models. Those formalisms can be used to mathematically specify your system and its requirements, and then you can use tools called model checkers to evaluate your system model and figure out whether or not it meets its requirements. These checkers do exhaustive analyses. It'll say, for any possible condition, will my system meet its requirements? And it'll evaluate every possible combination and sets of inputs. Now, for large systems with lots of different inputs and lots of different internal states, the formal method can't possibly exhaustively explore every possible combination of states. But research continues to go on in the area of formal methods in order to prove and verify whether or not systems work. Okay, MEC 7780, the course that is on the graduate level that follows this course, talks about making design tools, modeling tools, and does involve some formal methods for proving that your system does work. Okay, questions about designing systems on a high level like we've talked about today? Onward and upward. I hope you can all now design traffic light controller using state chart. No, I'm just kidding. You don't have to know state chart. Okay, now we're going to barrel on into programming in the small, which is Chapter 3. What Chapter 3 does is it gives you a high-level overview of the syntax of several different programming languages. Now, I have had students cuss the poor book about the fact that why are we learning Ada, why are we learning Occam, why are we learning Java, we're implementing in C, just teach me the C and let me forget about all these other painful languages. Trust me, no one wants to dump Java more than me. There are aspects about these programming languages that I need to teach you about. Why? Because there are ways of going about designing real-time systems that are better than what I'm making you do in the lab. The reason why I'm making you do the things in the lab the way that I'm making you do them is because I want you to be able to get a job. Okay? I want you to be able to function in industry, and I want you to be able to get underneath the hood and understand how the nuts and bolts work on an embedded system. Programming them in C makes you do that. Okay? There are abstractions, layers of the onion that smart people have put on top of these low-level nuts and bolts details that keep you from shooting yourself in the foot. And that's what these other programming languages offer, are constructs that force you to behave, so to speak, when you're programming an embedded system. So we need to study to some degree these other languages, and I want to expose you to them. Now, what I don't want to do is make you learn 4 new programming languages and have to be proficient at programming those 4 new programming languages. Some people in here would say, that is absolutely fantastic, I would love to do that, let's go. Other people would say, I'm out of here. Or as Rohit likes to say, window, when he wants to jump out the window. So I'm going to expose you to these programming languages. I'm not going to make you compile code in them. I might make you write code snippets in them, but I'm not going to make you compile code in Ada and Java. You'll be doing plenty of C programming in this class. Okay, so let's just go over a few of the common constructs between these languages. There's a lot of similarities in their syntax. There are differences, and you can kind of look at the language and say, well, that's not C, that's not Java, but there are artifacts that are similar. Some of the similarities between these languages are that they are block structured. Okay, programs are divided into blocks. Blocks facilitate declarations and statements. Okay, so if you look at Ada, here's your first view of Ada. Anybody know Ada? Nobody ever does. Okay, so first off, comments are 2 dashes followed by text. This is like the / in C++. Everything else after that is a comment. Okay, so you have the keyword declare in Ada, and then that's followed by a set of declarative statements. That's followed by a begin, and that's followed by executable statements, followed by an end and a semicolon. Okay, in the declarative statements, you declare variables. You have the variable name, followed by a colon, followed by a data type, followed potentially by an initialization. That initialization uses Ada's assignment operator, which is : equals, and then this A would be some variable that's been declared previously. So temp is an integer variable. It's being initialized to the value contained in the variable A. Then the executable statements inside the block, here we say A is assigned the value contained in B. B gets the value contained in temp. What does that do? A gets B, B gets temp. So A got temp. So let's just swap in the 2 values. Okay, here's C. We're not going to go into much in C. You already know about this. C has a block. The block is defined by an open brace and a closed brace. You first have declarative statements, followed by just non-declarative statements. Note, and many of you may not already be aware of this, in C you cannot have a declarative statement coming after a non-declarative statement in any block. All your variables have to be declared at the top of the block. Okay? So what that means is if you declare an int variable, then you have a printf, you can't declare another int after the printf. You can do that in C++, but you can't do that in C. Why? Because C was designed to support one-pass compilation. And in order to support one-pass compilation, you've got to know where all your variables are declared so you can define how big your stack frame is. We'll talk about that. You'll understand that better as we go on. Okay. How do you get around this if you want to declare a variable in the middle of a function? Okay. You can nest blocks. So int main, int I equals 0, printf. This guy is a non-declarative statement. This printf is. But what if I want to declare another variable after the printf? Well, I can just tag an open brace right there and have a closed brace after it, and I can declare an integer inside that open brace. Okay? So the open brace doesn't need to come at the beginning of a function. You can just put an open brace in the middle of your function, anywhere you want to, and define variables in there. And so you can nest these blocks. Okay? Okay, the other word about that is when you nest blocks, scoping of the variables you've declared within a block are limited to that block. So Java blocks work just like C blocks. Occam 2 is an older language, not as old as C, but it is a parallel language as opposed to a sequential language. There are specific things you have to do in Occam 2 in order to make things sequential. So every statement runs in parallel as its own process in Occam 2. So here, int temp colon. This says temp is an integer. The colon is a statement terminator, like a semicolon in C. SEQ is a keyword that says the following statements are all going to be run sequentially as opposed to in parallel. By default, they all run in parallel unless you tell it, I want the following block to be sequentially run. So let me say temp equals A gets B, B gets temp. So this happens sequentially. Okay. We want to, one note is that blocks define the scope of a variable. The scope is limited by the boundary of the block. Why do you want to limit the scope of the variable? it helps in organization, it helps in modularity, it keeps you from shooting yourself in the foot. Because if you limit the scope of a variable to a very defined small region in your code, then it keeps somebody else who's going to come over and maintain your code from inadvertently messing up your variable or assigning to it when you don't want it assigned to. Okay? So try to limit the scope of your variables as much as possible. That's the reason why they tell you never, never, never use a global variable. Because it's easy to shoot yourself in the foot. So with global variables, what I'm telling you in this class is it's okay to break that rule when you need to, but do it when you need to and know why you don't want to. It's to keep yourself from shooting yourself in the foot later on. Okay, variables. What's a variable? Anybody have a good definition for a variable? No one? No takers? Mitch, go ahead. I knew you'd take it.
A way for humans to keep track of.
A variable is a way. It's a process. It's a set of steps. A means.
By which.
A means is a mechanism. It's a machine. What is a variable? Okay. You're trying to say what you do with it. Don't tell me what you do with a variable. Tell me what it is. A memory location. Very good. A variable is a memory location. Yeah, y'all have been in, those of you in 3720, you've had this lecture before. Okay. A variable is a memory location. What is a variable name? A means or a mechanism or a shenanigans. It is an alias for that memory location. It's a way that I refer to that memory location. Okay? How big is the memory location of a variable? Depends on what the variable is. If I declare it as temp, how big is it? Okay, there we go. A little bit more specific. Okay, so it depends on the declared type of the variable. Okay, it also depends on the compiler that we use and the language you use. Okay, how about this? Int temp. What's the size of temp? Depends on the machine. Okay. So what if it's a 32-bit machine? What's the size of int? Still depends. What do we mean by when we say it's a 32-bit machine? Those of you who have had this lecture before. The number of bits in the address space. So if it's a 32-bit machine, that means the address bus is 32 bits on it. So that mean, what does that mean? You've got 32 address bits. 2 to the 32 different memory locations you can address. Okay? Does that tell you how big an int is? Does it tell you how big a pointer to an int is? Yes, it does tell you how big of a pointer to an int is. It does not tell you how big an int is. Okay, so we have 32 different slots. Each one can be a 1 or a 0. That means we have 2 to the 32 different locations that we can address. So a 32-bit machine means we have 4 gig addresses. On a 16-bit machine, we have 64K addresses. How big of a chunk of memory does each unique address address? So on an x86 machine, one address, how big of a chunk of memory does each address point to? Does it depend on if you've got a pointer to an int or a pointer to a char or a pointer to a double? Does memory care what data type it stores? No. What does memory hold? 1s and 0s. And how big a chunk? x86 is a byte addressable machine. That means each chunk is 1 byte. Each address has its own byte. There are machines that are not byte addressable. you have the TIC40 DSP, which is quite an old processor now. This was mid-90s where this processor was out. But it is a word addressable machine. That means each address points to a word. And on that machine, it was a 32-bit machine, and it declared its word size as 32 bits. So every address on the machine pointed to a 32-bit memory location as opposed to an 8-bit memory location. On an x86 machine, when you declare an int, it takes up 4 addresses. Okay? Why then is not, when you declare a pointer to an integer, why isn't that an array of 4 different numbers? If your integer takes up 4 addresses, how come a pointer to an integer is not 4 different addresses? Or is it? Very interesting conundrum. Okay, you remember your 8088 machine? You have that you were doing in 3710? You had separate address and data buses. Your word size is the number of bits in your data bus. Your address size is the number of bits in your address bus. Okay? You can have a 16-bit machine with a 64-bit data path. So size of int is the default width of your ALU, typically. But things get muddy when you start talking about 64-bit machines because they have compatibility modes with 32-bit machines and so forth. So typically, on a 32-bit machine, you're dealing with a 32-bit int. Basically, size of int is 4 on a 32-bit machine. It's 4 for a WinXP 32-bit box. It's 4 for the TS7200. 4 what? 4 bytes. 4 bytes on a 32-bit byte addressable machine. 1 int covers 4 different addresses. We'll talk about that in a bit. What type of information do I store in an int? Bits. 1s and 0s. Okay, memory doesn't care what it stores. It just says, I'm going to store 1s and 0s. It just maintains those 1s and 0s. Talk more about this next time. You raising your hand, Garrett? Yeah, you can work in pairs on the lab. Okay, so if you're working with a partner on the lab, you both have to submit something. The something can be identical, and it should have both your names on it, but you both have to make a submission under Blackboard. Otherwise, that'll mess up the grading. And you want to get Lab 2 going already, huh? It'll be posted shortly. Jonathan.